Hello, everyone. Thanks for joining our webinar. My name is Rachel Williams, and I'm JA King's Business Manager for Motorized Vehicle and Aerospace. Joining me today is Casi Noel. Casi is the site manager for JA King's embedded operation at the Nissan Powertrain Assembly Plant in Decherd, Tennessee.
Thanks, Rachel. Today, we're going to discuss some of the torque-related pitfalls we encounter as well as some tips for implementing a quality torque program.
As you may know, JA King has a tremendous amount of torque measurement expertise. We are familiar with fastening applications in a variety of industries, including automotive, obviously, aerospace, and oil and gas. Today, we'd like to discuss some common torque problems, tips for precise torque control, and provide a solution example of a quality torque program. We'll also leave some time for questions at the end, so feel free to type those into your chat function. Let's get started with a brief review of some torque basics. Torque is a force that produces rotation. It's determined by the magnitude, direction, and the location of the applied force. In manufacturing and assembly, precise torque control helps ensure that you're producing safe, reliable, and high-quality products. Today, you may also hear us discuss static and dynamic torque. Static torque refers to torque measured after the tightening process has been completed. Typically, this is done with a torque wrench. Casi actually started as a QC tech at our Nissan Smyrna operation, so she was very concerned with static torque measurement in her day-to-day job. Static torque may also be referred to as breakaway or residual torque. When we talk about dynamic torque, we're referring to torque that is being measured continually during the tightening process. This can be accomplished a couple of different ways. You can do it directly with a built-in or inline transducer, or indirectly through current measurement with some DC torque tools. Now let's talk about some factors that affect accurate torque measurement and can potentially lead to fastening errors.
Torque issues are due to one of four factors: man, the operator; machine, the torque tool being used; the method, or the materials. Let's look at each of those individually. Okay? Two examples of operator-induced torque errors are running a tool down at the wrong speed, either too fast or too slow. The second has to do with misaligning the torque tool and the bolt. Fatigue may also cause the operator to hold the tool sideways versus lining it up straight with the bolt. This is known as cosine error and can also be a factor in torque tool calibration in addition to assembly.
Some pitfalls are due to problems with torque tool is using the wrong tool for the application. Second is neglecting routine calibration. Torque tools will diverge from their proper settings over time.
It is especially important that a tool is recalibrated immediately in the event that it's dropped.
Okay, that's great to know. Another torque tool related issue is neglecting preventative maintenance. Excessive wear or defective parts can result in inaccurate readings and cause unplanned downtime. Finally, the tool can fail. For example, you could have a tool with a damaged transducer, cable, or connector, and that display on the tool may still be displaying an OK torque reading when in actuality it's not.
Torque issues can also be related to material conditions. For example, weld plugs, fillets, or paint can create conditions in the joint. Also, changing parts, suppliers, or part tolerances, even if the new part is still in spec, can also lead to fastening issues.
Finally, errors can also result from the method that you use. For example, the majority of joints consist of multiple bolts that are bringing together two surfaces that aren't perfectly flat. If you don't follow the proper tightening sequence, it can result in an uneven preload distribution. So if you look at our fabulous drawing that one of our engineers did for us very early this morning, you can see the crisscross tightening sequence. So typically this is specified when you have circular bolt patterns. For non-circular bolt patterns, we recommend a spiral sequence, and then with that, you'll actually start in the middle before spiraling outward. Now that we've addressed some common torque pitfalls, let's discuss some tips for precise torque control. The first tip is selecting the right tool for the process. There are a wide variety of torque tools available on the market, from click wrenches to pneumatic screwdrivers. So here are some important factors that you can consider when you're selecting a torque tool. First of all is the amount of torque required. It's important to note that you should select a tool where the specified torque range is mid-range for the tool. What I mean by that is if your torque specification is 20 newton meters, you would want to select a torque tool whose range was from 8 to 40 newton meters. It's also important to consider the type of materials that are being joined, your joint stiffness, the speed required to meet your cycle time, and also ergonomics for the operators.
It's also important to ensure that operators are properly trained on how to use torque tools and tightening strategies. For accurate torque measurement, operators must apply flow to the center of the handhold position. Moving off center can produce errors.
Our third tip is to establish an effective calibration program. Routine calibration ensures that torque tools are accurate and repeatable. We often get asked about determining calibration intervals. To do that, you should consider how critical that particular torque measurement is, and also take into account the tool manufacturer's recommendations for calibration intervals.
We also recommend implementing a preventative maintenance program. PM prolongs the life of tools and identifies minor issues before they become major problems, helping you avoid downtime. PMs performed by J. King include breakdown of the tools, inspection, relubricating, and rebuild if needed.
Our final tip is to collect torque data and use it to drive decision making. For example, J. King currently has 7 embedded locations, like where Casi is in Decherd, where our technicians are performing torque tool calibration, preventative maintenance, repair. They also do QC audit and line call support. We track all of that torque data and provide it to our customers so that they can make informed decisions. We track that data by process, by the tool model, and by the time. So let's get into that a little bit more. Tracking by process helps determine if either you're using the incorrect tool for that process or if there is an issue within the process that is causing unnecessary abuse on a particular torque tool. Tracking by tool model can help determine if there might be issues with a specific tool model. One of the benefits of using J. King is that since we do have all these different embedded sites, we have a lot of data on common torque tool models, and we can pull that across sites. We can use this information to help you communicate to the tool OEM to determine corrections for future revisions and decide what equipment you need to buy in the future. And then tracking that history by time can help identify if there is a certain shift or maybe a certain operator during a shift that isn't using the tool correctly. So the amount of data that we collect helps customers track the total cost of ownership for their torque tools. As I mentioned before, we have several customers that essentially drew a line in the sand and decided that torque measurement was so important, they were going to let a world-class measurement provider handle those torque measurements and the calibration and the repair. Casi is going to describe a certain situation, a solution example that she's encountered in her role in the embedded site about how we have implemented a quality torque program for our customers.
So for example, an operator is securing a bolt in a critical process. The operator drops the tool in between units. He picks it up and secures the next unit in line and sees that it shuts off at the desired torque and the display shows okay. 30 units later, the J. King quality control technician performs her scheduled check on the fastener and finds a static torque outside of the allowable tolerance. At this point, the fastener is identified as loose, and a calibration technician is called to verify that the tool is still in calibration. The calibration technician confirms that the tool is damaged and the output is significantly lower than the desired output. An embedded repair technician responds to the line and identifies an internal transducer on the tool is damaged, causing it to read incorrectly. The repair is made line side and the tool is placed back into service. The calibration tech and the quality control tech immediately verifies that the tool is repaired and in calibration. With our embedded services, the customer only needs to contain 30 units. However, without the quality control, the operator still receiving an okay reading could have left this until their tool scheduled calibration due date. If the issue occurred early in the calibration cycle, this could have resulted in a significantly larger issue.
So essentially, without a robust work quality control program, say that the tool just been calibrated 4 weeks ago and it was on a 6-month interval, you may not have even known that that tool was out of tolerance for 5 more months.
That's right.
Yeah, that's a great example. If you're interested in learning more about our torque capabilities, and especially our embedded services, please be sure to visit jaking.com. We have a lot more information about the services we provide, and some examples. So at this time, we would like to open it up for a few questions. So I'm going to look to Colin off screen and see if we've had any questions submitted.
All right, yeah. So what types of torque tools do you repair?
Well, we repair all makes and models. In our embedded sites, Jay King works diligently to perform as many repairs as possible on site. When we repair a tool, we document the problem found, the description of the repair, and the parts usage. We also help our customers determine if tools are beyond economical repair.
So when we talk about beyond economical repair, we're basically saying, because we do this in the full service branches as well, if you send in a torque tool or really engaged for calibration, and we find that it requires repair. Say it's a $1,000 tool. If your repair is going to be $800, we communicate that to you and let you know that in that case, it may just be better to purchase a new tool versus paying that much money to repair it.
Okay, so another one that we had was, how do you track torque calibrations?
So in both our full service branches and in the embedded sites for KCS, we use our calibration software called Gauge Suite. So one of the benefits of using Gauge Suite is that it tracks all the activities. So that includes PM, if we're doing a repair. But in terms of calibration, it gives you a robust recall system. So you can ensure that you are not missing a calibration due date for your tool. And then it also provides the calibration certificates and all the information you need for traceability in one spot.
Okay, so here. So it's cheaper to get a new torque wrench than to have it recalibrated. So why wouldn't I just want to get a new torque wrench?
The main reason you wouldn't want to just get a new torque wrench, you would actually want to send that torque wrench off to be calibrated, is, like we mentioned before, for traceability purposes. So say that torque wrench is on an annual interval, and say, like in our solution example, it was dropped 7 months ago by an operator. You don't have any of that traceability information to know that for that whole time period you were using that torque wrench and it was out of tolerance. So I would say, yes, you may be able to get a new wrench for $250, but you don't have any of that information without sending it back in for calibration.
All right. I'm interested in embedded services that don't have many tools. Is there a required minimum for JSC?
No. So when we start discussing embedded, there are a couple of situations where that happens. We have some current customers where their annual calibration and repair spend gets to be about 6 figures. At that point, we will come to them and say this may be a scenario where an embedded solution could benefit you. But our embedded sites range from one technician who works part-time to, Casey started at Smyrna where you have, how many was it?
I was one of 70 technicians.
So typically, if embedded is something that interests you, we would love to talk to you, and we typically set up a site visit to discuss, what does the scope of work look like? What do you want us to do? Or you want us just to do solely calibration? Are you interested in QC audits, line call services? And then we'll will look at your tool population, your intervals, and make some recommendations to you on how often you need to have a technician on site if it's full-time, and then how many technicians if your tool population is quite large.
So this one kind of relates to that. So our facility currently has J18 in Omaha serves our scales, because we have our torque tools calibrated on site by them as well.
It depends on the torque tool, but more than likely you can. We can definitely get you in touch with your local account manager. That is one benefit. You know, I'm out talking to customers who can do a lot of torque tool calibrations on site, which is a benefit. A lot of places I go outside of the embedded sites that are serviced by a full service branch, they may be using competitors for torque tool calibration services, and they're having to box up all their torque tools and send them out and have spares. Whereas we can likely come on site and do them on site.
Awesome. So for in-process calibration, so say verifying in that runner, how do you safely perform the rundown for higher torque values? So what torque value is considered unsafe to perform a rundown checking process?
And I think
Not the maximum.
I'm not aware of one.
Yeah, I'm not aware of one.
Okay. On a manual foot type torque wrench, what's your opinion in double clicking once the wrench clicks? So let the fastener rest and then reapply force to the wrench and make it click again. So on a manual foot type torque wrench, what's your opinion in double clicking? So that is once the wrench clicks, let the fastener rest and reapply force to the wrench and make it click again.
It's called a high,
Yeah, that could,
high tolerance torque.
yeah. So I would not double click because that's going to cause your static torque to be high.
All right, looks like that's what we've done so far. So if anybody else has any questions, we're good to go.
All right. Okay. Well, thank you so much for taking time out of your day to join us. We really enjoyed it. If you think of any other questions, feel free to reach out to us. My email, if you have any questions, is rachel.williams@j18.com, or you can always contact